In this video, I'm going to do a bunch of examples for Newton's second law. In the first example, I have a 50 kilogram rocket accelerating upward at 2 meters per second squared, and I want to know how big is the force due to the rocket's thrust. So to begin with, I'm going to draw a free body diagram. I know that the rocket will have some weight pulling it downward. That will equal mg. So that's 50 kilograms times 10 meters per second squared, or 500 newtons. Right. There is also a force due to the thrust acting on the rocket. This is the thing I want to know. And the other thing I'm told is I have an upward acceleration of 2 meters per second squared. So now I take F net and let it equal ma. Mass is 50 kilograms. Acceleration is 2 meters per second squared. I didn't say it, but I think it makes a lot of sense to let the upward direction be positive because that is the direction of the acceleration on this rocket. Okay, 50 times 2 is 100 newtons. I can rewrite the net force in terms of the forces on the rocket. So I take all the forces in my positive direction, subtract off the forces in the negative direction. So that means the force due to the thrust minus 500 newtons equals 100 newtons, or that the force due to the rocket's thrust is 600 newtons. For my second example, I have a 3 kilogram toy car. It is pulled to the right at an acceleration of 5 meters per second squared by a 6 Newton force across a carpeted floor. Okay, how big are the 4 forces including the pull on the car? So we have a normal from the floor on the car. We have gravity pulling downward. This one, of course, is mg, which is 3 kilograms times 10 meters per second squared, which is 30 newtons. We are told that we have a pull. It's probably a tension, but we don't know, so I'm just going to call it the force from the pull, but this is a 6 Newton force. And for the fourth force, it's carpeted. That means there's got to be friction. Okay, and we want to know how big are our 4 forces. We have 2 of them already. This one we were given. Weight we can calculate using mg, which we've done. The car is not flying off the floor, it's not sinking into the floor, therefore it's not accelerating upward at all. That means the normal force between the floor and the car and the weight have to equal each other, which leaves us one force to find. In order to use that force, I need to use the knowledge that the acceleration is in the direction of the pull and equals 5 meters per second squared. So I let F net equal ma. The mass is 3 kilograms. The acceleration is 5 meters per second squared, which is 15 newtons when you multiply it out. I can rewrite the net force in terms of the forces on the car. Everything in the positive direction, that would be the pull, minus everything in the opposite direction, which would be friction. So that's 6 newtons minus the force of friction equals 15 newtons. I'm going to leave this minus sign and just bring it down. I need to get it by itself, so I need to subtract 6 newtons from both sides. So that is a 9 Newton force. 15 minus 6 is 9. And now I see that I have made an error in this problem, but that's okay. I got a negative sign out for my friction. Right? And that negative sign means it's in the opposite direction, which means my 6 Newton force is not big enough to actually accelerate this car as much as it needed to be. That's my fault for writing the problem. What can I say? We'll just call this one an oops. Nothing wrong with the math, just a problem with the numbers that I chose. Okay, example 3. We have a crane lifting a box upward with an acceleration of 2 meters per second squared. We're told that there's a tension of 10 newtons in the rope, and we want to know the box's mass. So here is my box. We have a tension between, say, a rope and the box. We have gravity pulling it downward, but we can't calculate that yet because I don't know the mass. I do know that this force is 10 newtons, and I know that I have an upward acceleration of, boy, I really like 2 meters per second squared for these examples. And let's let up be positive. So F net equals MA, but I can't plug in for MA yet because I don't know M. What I do know is I can rewrite the force, the net force, in terms of the forces acting on the box. So that's tension minus weight. I take everything in the positive direction, subtract off everything in the negative. I know tension is going to be 10 newtons. Weight will be mg, because that's what it is. And that equals ma. Now I need to do some math here to get all of the masses on one side of the equation. So I'm going to let 10 newtons equal ma plus mg. Now I can factor out a mass from each piece, so that's mass acceleration plus the acceleration due to gravity. Right. So that's my mass. My acceleration is 2 meters per second squared. The acceleration due to gravity is 10 meters per second squared. Now watch out. Do not plug that in as a negative number. You've already got the negative up here, right? G on its own is a positive number. Okay. So mass times 12 meters per second squared equals 10 newtons. And if you put that into your calculator, 10 divided by 12 is 0.83. So the mass equals 0.83 kilograms. We have a toy train accelerating to the right at 1 meter per second squared. We are given the force the engine is providing. We're given the force of friction. We want to know the train's mass. So there are 4 forces on the train. We have a normal between the track, let's call it the rails in the train, just so we don't have 2 T's. We have gravity acting downward. We have the force due to the engine, and we have the friction between the rails and the track. The acceleration is going to be to the right, and I'm also going to let to the right be positive. I can't calculate the weight because I don't know it, or I don't know the mass, and I don't know the normal force, except I know it's equal to the weight because I don't have an acceleration in that direction. Using Newton's second law, F net equals ma. I can't calculate ma yet because I don't know the mass. That's what I want to know. What I can do is rewrite the net force in terms of the applied forces. So that's the force from the engine minus the force of friction. That equals ma. I'm told that the engine is giving a 6 Newton force. Friction is 3 newtons. I don't know mass, and the acceleration is 1 meters per second squared. The first thing I need to do is subtract, so that's 3 newtons equals the mass times 1 meter per second squared. Now I can divide out the acceleration, but dividing by 1 is trivial, so the mass is 3 kilograms. For my last example, I have a table and 2 blocks. And everything is accelerating upward at 1 meter per second squared. I have a blue block on the bottom and a red block on the top. And I want to find 3 forces. The force between the red block and the blue block, the force between the blue block and the red block, and the force from the table on the blue block. So I'm going to draw 2 free body diagrams, one for each block. So to begin with the red block, I have a normal from the blue block on the red block, and the gravity pulling down caused by the Earth. On the blue block, I have a normal from the table on the blue block. I have gravity pulling downward, and I also have a normal force from the red block sitting on the blue block. So the 3 forces I want to find are this one, and that one. Okay. If I look at the blue block, I realize I can't do anything really here because I don't have enough information. There are 2 unknown forces. So I'm going to start with the red block. The red block has a mass of 1 kilogram. The acceleration due to gravity, or not the acceleration due to gravity, the acceleration is 1 meter per second squared. And writing it in terms of the applied forces, the weight, remember, is mg. So that's going to be 1 kilogram times 10 meters per second squared, so that's 10 newtons. Okay, so we have normal minus 10 newtons equals 1 newton, which means my normal equals 11 newtons. Okay. So that's this force. Now I'm going to pay attention to this force versus that one, and I see they're the same type of force. They have flipped subscripts. They act on 2 different objects. They're in opposite directions. This is a third law force pair. Therefore, I can immediately write down that this one is also 11 newtons, and I can make a little note to myself that that's because of third law. Finally, to find the normal between the table and the blue block, I can look at the blue block. First thing I'm going to do is calculate the weight. It's a 2 kilogram blue block. Acceleration due to gravity is 10, so that's a 20 newton weight. Okay. The mass again is 2 kilograms. The acceleration is 1 meter per second squared. I take everything in my positive direction, and I didn't write it, but I have assumed it that up was positive, so I'll make a little note of that now. So that's the normal minus the weight, and then also minus the other normal, because these 2 are both in the negative direction. Okay, so the normal minus my 20 newton weight minus this guy, which is 11 newtons, equals 2 newtons. So the first thing I need to do is add 20 and 11. 20 and 11 added together is 31 newtons, equals 2 newtons. The next thing I need to do is add 31 to both sides. So my normal equals 31 plus 2, which is 33 newtons.